wanted to talk this morning about differential equations, but I also wanted to make sure that we're talking about this idea of propagated error. And I guess the best example I can give you would be, well, let's take this ball bearing right here, if you will. So this is my ball bearing, and I'm going to measure it, and I want to figure out, well, exactly how big around is this thing. So I'm going to maybe take this caliper device. Maybe it looks like this. I don't know. Let's change colors, make it something pretty. This caliper device right here is going to maybe look like this. And it's going to have this big arm thing on it, right, and a handle that kind of screws it, in, right? And maybe a little thing at the end to turn it with. And it's going to have this other piece that it's going to come jutting through here. It's going to open up like this, right? And then this device is going to turn, and at the end of all of it, we're going to find out, well, how big around is this ball bearing? So here's our little device. And what I'm suggesting to you is that the measurement, no matter how exact, will still be imprecise. And that's what we're going to talk about. So I'm going to kind of say this, like, let x represent the measured value. And then let x plus change in x equal the exact value. So x plus change in x equals exact value. Well, then how far off is our measurement? Well, I think our measurement is off by change in x equals the error, doesn't it? It's the error in measurement. Not the error in how we built this thing, but the impreciseness of the vehicle, of the machine with which we're measuring by. And sometimes this is incredibly significant, right? Sometimes this is really, really significant. You take stuff like the space shuttle, and we can talk about some catastrophes that have happened, and we can argue about where the tolerance is tight enough, where the measurement's exact enough, and it's something to argue about. I think we can leave it at that. So let's look at this idea of propagated error. So our propagated error would actually look like this. We have our f of x plus change in x, right? Minus our f of x would equal our propagated error, change in y. And this is about as far as I'm going to go with this right now, because in the next video that I'm going to cut in like 2 minutes, I'm going to start talking about real problems. But this is the one I want to start with, just the idea of kind of putting the nuts and bolts together. So we agreed that this is the exact value, right? This is the measured value here, isn't it? And then, of course, this would be our propagated error, right? And this is our error in measurement. So this is what I wanted to start with, because we have to build this thing. We're going to have to build this thing and make it do what we want it to do. So that's how I wanted to start. Plus, I wanted to color this thing in really badly. I just want to color this in. So I'm coloring. Oh, you're like, the guy's an idiot. Well, maybe he is. Okay, so this is our intro to propagated error. Please watch the next video, because I'm going to do this. We're going to do this problem on measuring this ball bearing and seeing what the propagated error would be. So thanks for watching. If you haven't already subscribed, please do. And I tried to keep this video really short, so hopefully you're still with me.